So, yes. Okay, hi everyone, and I'm Chen, and today I'll talk about our recent work. What does this mean? Is this the wrong one? I see. Okay, great. Okay. Yeah, hi everyone, and today I'll talk about our recent work, the post-quantum security of the Even-Mansour Cipher. And this is a joint work with Gorjan, Alagic, and Jonanthan, Katz, and Christian Majenz. So let me start with the motivation of this work. And as we know, quantum computers will have a big impact in crypto, and many commonly used crypto systems will be completely broken once large quantum computers exist. Well, in asymmetric cryptography, which uses a public key to encrypt data and a different key private key to decrypt data, since Shor's algorithm can solve the factorial problem in polynomial time, many asymmetric primitives such as RSA and DK-Hellman, which based on the hardness of such problem, totally insecure in the quantum world. And moreover, it seems feasible for a malicious attacker to simply store all the encrypted data when it has access to a quantum computer. So switching to like lattice-based and code-based schemes is also very important. And the next main part of cryptography is the symmetric crypto, also called the private key crypto, which uses a SIM key to encrypt and decrypt data. And our work mostly focuses on the symmetric crypto. And in the quantum world, the most common quantum attack for symmetric primitives is based on the Grover's algorithm, which provides a quadratic speedup for searching an another database. So here comes a very straightforward solution. You can just double the key length to cover this quadratic speedup. But the question is this enough? Or does there exist any currently unknown clever quantum attacks? So recently, crypto scientists are making some progresses on quantum attacks using superposition queries. And some attacks that seem actually perform better than Grover, and it actually just require polynomial queries. But all those attacks can rely on the quantum access to the key function, which is hard to achieve. So, so the question is still here, is symmetric crypto safe in the quantum world? And to answer this, the goal is to design a toolbox of symmetric cryptanalysis in a quantum setting in order to understand the security of symmetric algorithms against quantum adversaries. So next, I'll talk about one key ingredient in the symmetric crypto, which is the block cipher. So block cipher is just an encryption and decryption scheme which works, which operates on blocks of data. And here, this picture shows how it works on a single block. So it has two parts: the encryption part and the decryption part. And classically, the block ciphers are very commonly used. And for example, the most commonly used block cipher, which is the one encryption standard. And also block cipher modes are commonly used to provide information service, such as the confidentiality and authentication. And here are the examples. So apparently, block ciphers are very well studied and well used classically. So now the question is, are they secure against quantum adversaries? So I guess this part haven't been answered a lot. So to study this, we start with one simplest block cipher, which is called the Even-Mansour Cipher. And Even-Mansour Cipher is just a general construction from for a block cipher. It's just a general construction of a block cipher from a publicly known permutation. So here is the definition and the sketch. This is a minimum construction since the block cipher EK is constructed only from one public permutation P and with two XOR operations. And it has been proved that eliminating either one of the two XOR operations makes XOR keys make it easy to recover the other one. So basically, can't make it simpler. And Even-Mansour is actually widely used in many symmetric key constructions. and for including some like lightweight, needs lightweight candidates. So so next I'll talk about the quantum attack models. So in the symmetric setting, so quantum attacks can be mainly classified into two types. And the first model is a Q1 model, where attackers have access to a quantum computer to perform any offline computation, where they are only allowed to make classical online queries. And in the Q2 model, the attackers have access to a quantum computer to perform any offline computation, and they are allowed to make quantum queries to all oracles. So applying those two models to the Even-Mansour, and the Q1 model refers to the case where the adversary has classical access to EK and quantum access to P. While in Q2 model, the adversary has quantum access to both oracles. So one important thing to note is that since P is a pop permutation, so it can be specific by some like publicly known circuits, which means so it can be implemented locally by an adversary. So the adversary can just get its circuits and implement the unitary operators to get the quantum access locally. Well, in contrast, since EK involves the private key, which is unknown, then the adversary can't get such access to the circuits. And the only way the adversary can possibly get quantum access to EK is by would be if there is exists some quantum interface to grant such access. However, since the keyed encryption EK is implemented between honest parties using a classical computer, so apparently, there's no way for honest party computer to expose a quantum interface. And with all that said, Q1 model is much more realistic and natural than Q2 model, even when the large quantum computers exist. So next, Q2 model is not what we want. And next, I want to talk about the security of Even-Mansour. And so first, it is classically secure with optimal attack QE times QP, at least around 2n. So this proof was first given by Even-Mansour and then later evaluated by others. And next, in the Q2 model, unfortunately, this is totally insecure against a fully quantum attack. And in that setting, the adversary can just evaluate the unitary operators like UP and UE here for P and EK on any quantum state it prepares. So to see how it is insecure, let's take a look at the EK XOR P. And this has a hidden period K. So which means we can just apply the Simon's algorithm to give an attack using only polynomial queries to find the K. And that's the high level idea. Right, and next in the Q1 model, and the secure wasn't clear yet. So previously, Kuakato and Mori showed the key recovery attack, which only requires 2 to the N-3 queries in total, and using the BHT collision finding algorithm. And their attack requires exponential memory, which was later improved to polynomial memory in the offline assignment work paper. But all those are attacks, whether the Even-Mansour construction is secure in the Q1 model hasn't been answered yet. So our work answered this question, and we proved a lower bound showing that 2 to the N-3 queries in total are necessary for attacking the Even-Mansour Cipher in Q1 model. Right, so next I'll talk about our result. So here is our main theorem, where if you take a look at the equation, and on the left-hand side, and so the adversary has classical access to the Even-Mansour Cipher EK and quantum access to the public permutation P. So we call this the real world. And on the right-hand side, the adversary has classical access to a uniform permutation R and quantum access to P. So we call this the ideal world. And now, so basically theorem 1 shows for any attacker who wants to distinguish those two worlds with constant probability, the attacker needs either QE squared times QP or QP squared times QE at least 2 to the n. So that implies for any attacker, any attacker needs at least 2 to the N-3 queries to attack Even-Mansour ciphers successfully in the Q1 model. And our theorem works for an adversary who can adaptively choose how many queries it makes based on the outcomes of intermediate measurements. And also, in our theorem, the adversary has both forward and inverse query access, since P is a permutation. And in this talk, I'll basically just focus on the forward case, and probably I'll ignore the inverse case, but we prove that the inverse case is totally symmetric. Okay, so next I will talk about a little bit about proof, and I want to start with the two essential lemmas we need in our proof. And the first one is the resampling lemma. And so this is like the permutation version of the previous work, which is called the adaptive reprogramming lemma. And it works for the function case. So here we extend it to the two-way accessible permutation case. So we start with a uniform permutation P and the two-phase distinguisher P. The goal of the distinguisher is to determine whether the permutation was resampled or not. So right now let's start to look at how the resampling game works. So let's start with phase one, where the distinguisher just gets quantum access to P and its inverse. After making Q0 queries, it outputs a state as T. So before the second phase, now the challenger samples a uniform bit little b, and along with two uniform n-bit strings S0 and S1. And then the challenger construct a set P0 as the original permutation and P1 as the resampled permutation, where basically just swap the value of the output of P0, S0 and S1. So basically just swap the value of PS0 and PS1. And then the challenger set is resampled permutation as P1. Now in the second phase, the distinguisher receives the quantum state 0 and S1, along with the quantum access to PB. And after making Q1 queries to PB, it outputs a guess B prime. So the distinguisher wins if it guesses the B correctly, which means B prime equal to B. And intuitively speaking, since the resampling values S0 and S1 are from the same distribution used to initially sample the outputs of P, so basically the distribution doesn't change after resampling happens, which means the only way the adversary could win this game or tell whether the permutation is reprogrammed or not is by querying either S0 or S1 in the first phase. So right, with only classical size, it needs to make 2 to the n queries in the first phase. And our resampling lemma shows for any quantum adverse distinguisher D, right, the distinguisher needs to make like at least root to the n queries. So there is at most a quadratic speed up. Right. So next, I want to talk about the arbitrary reprogramming lemma, and this is the generalized version of the blending lemma in the previous work. And here, this lemma works for an adaptive adversary. So it involves a 3-phase distinguisher, and the goal of the distinguisher is just to determine whether an arbitrary function was reprogrammed. So let's start with phase one, where the distinguisher simply outputs the descriptions of an arbitrary function f and the randomized algorithm b. So script b. So if you run the script b, you get output a set capital B. And the probability of each element in this capital B is at most epsilon. So here, the distinguisher has a full access to the function f. It knows exactly what the function is, and she can actually select how the function will be reprogrammed based on the choice of the random algorithm script b. So to see how it works, let's take a look at the second phase. And before the second phase, the challenger just sample a randomness R and use this R to invoke the algorithm script B, and so that it output a set capital B. And then the challenger samples a uniform bit little b. Now, similar as the resampling game, the challenger set construct a new function fb, where the output of each x in B is reprogrammed to y. So the challenger set f0 as the original function and f1 as the reprogrammed function. Now in the second phase, the distinguisher just gets quantum access to fb, and after making Q queries in expectation, it outputs a state as T. Right. So when the distinguisher is done making queries, here we have the phase 3. Now it receives the randomness R using the phase 2 along with the quantum state. And then the distinguisher output the guess B prime. So distinguisher wins if B prime equal to B. And intuitively speaking, the only way the distinguisher could tell whether the function was reprogrammed or not is by querying with significant amplitude on some points in set B. So that happens in the phase 2, right? And since the probability of each point in B is at most epsilon, make 1 over epsilon queries. And our arbitrary reprogramming lemma shows for any quantum distinguisher D, there's at most a quadratic speed up. I want to talk about the proof. So yeah, as we have seen the theorem 1, the goal of the theorem is just to prove the real world is closed. Between the first and the last hybrid by making slightly changes hybrid by hybrid. So here we want to get our final hybrid QE from H0. So we added many intermediate hybrids and we make small changes each step. So here all the H1, H2, all the way to QE minus 1 are all the intermediate hybrids. And we're going to prove each intermediate hybrid is close to its previous hybrid. So to see how it works, let's take a look at the first hybrid, H0, where each EK or R indicates one classical query and each P indicates multiple quantum queries. And without loss of generality, let's suppose the classical queries are non-repeated. So basically, H0 is just like a QE stage hybrid, where the stages are divided by classical queries. So for example, this first stage is just it corresponds to a period between the first and the second classical query. And here, the adversary can adaptively choose how many queries she makes in each stage. And in total, so here, that's why our theorem works for an adaptive adversary. And in total, the adversary makes QE classical queries and QP quantum queries. So right, our goal is just to get HQE from H0. So basically we need to change every EK to P to R, right? So we do this step by step. So our first hybrid H0, H1, where we just change first EK to R and keep everything else unchanged. So right, following this idea, and we change the second EK to R, and we get H2, and so on. So after QE rounds, we get our final hybrid H2E, where all big classical queries are answered by a random permutation R. So right, this is the general idea of our hybrid method, and our next goal is just to prove that H0 is close to H1 and so on. But right, in this construction has a problem. So to see how the problem is, so suppose in the first classical query, the adversary input is 1 and get output y1. So in H0, x1, y1 has such connection based on the definition of Even-Mansour Cipher. Well, in H1, x1 and y1 is just a random pair since R is a random permutation. And here comes the problem. So imagine there's an adversary who can actually learn the key in later rounds. Then the adversary can just, so now the adversary knows x1, y1 and the key. Then the adversary can just easily distinguish those two hybrids by querying x1, x or k to the quantum oracle P, right? Because then in H0, it'll get y1, x or k. And in H1, it probably gets something totally independent from y1. So what I want to say is that, like, if we want to disprove that H0 is close to H1, it kind of already needs like the condition that Even-Mansour is secure. So the adversary won't learn the key. So that's not what we want, right? Because we want to, like, we don't know it's secure or not. We want to prove this, whether it is secure. So to overcome this problem, we added one more intermediate hybrid, which is H0 prime. And the difference between, and in the H0 prime, is still the first classical query is answered by R, but all the other quantum queries are answered by PP1K instead of P. So, right, as shown on the right-hand side, so P1K is just a reprogrammed version of P, whereas the output of X1K is reprogrammed to Y1K. Because, so now, H0 and the H0 prime looks identical to the adversary's view. Even the adversary can learn the key, because when you query x1 XOR k to the P oracle, both will get y1 XOR k as the output. So in this way, we can prove that H0 is close to H0 prime. And also the only difference between H0 prime and H1 is that first quantum query is answered by PT1K instead of P. And we are also able to prove that this change is relatively small. So, so this is the idea of our hybrid method and how it works in the first round. So let me, since I don't have enough time left, but just so here is the general case of our hybrid in the Jth round. And we have the corresponding Hj and the Hj prime. So this is just the extension of H0 and H0 prime. And we prove for every J, Hj is close to Hj prime. And we prove that by constructing a resampling gain. So the bound actually comes from the resampling lemma and along with some bad events we encountered. And also we are able to prove the Hj prime is close to Hj plus 1 for every J, and by constructing an arbitrary reprogramming gain. So the bound actually comes from the arbitrary reprogramming lemma. So if we combine those two results together, we can actually prove Hj is close to Hj plus 1 for every J. So that satisfies the goal of the hybrid method. And if we add up all those results together, we can finally get our bound for the theorem 1. And we prove that the H0 is close to H0 HQE. So so this is an oversimplified version of our hybrid method. So now let me just summarize this talk. So block ciphers are key ingredients in symmetric crypto, but the quantum security of classical secure block ciphers in the Q1 model are mostly unclear. So in our work, we focus on one simplest block cipher, which is the Even-Mansour Cipher, and we prove the quantum security of this cipher in the Q1 model. So at least to the number 3 queries are necessary to attack. Yeah, so that's it. Thanks everyone for listening.
We have some time for questions. Thanks for the talk. Do you think this kind of proof could be adapted to similar constructions, such as the FX construction?
Right. Right. We also thought about the FX construction also, and this is kind of like an ideal cipher model, but the only difference, so Even-Mansour Cipher is just kind of like a special case of the FX cipher, where FX construction involves the a FX key and a cipher key, right? So the cipher key is 0. This is the Even-Mansour case.
Yeah.
And I think we haven't done this yet, but I think this is a great extension to this work. Yeah.
Thank you.
Thanks. Thanks.